Okay, I'm going to take you through a bunch of problems from Chapter 8 as a little bit of a review, identify some of the key concepts. First of all, we have multiplying and dividing by rational expressions. This is a really complex rational expression where I got a double fraction, a fraction over a fraction essentially. The key to these, factor whenever you can to look for things to cancel. If you're divided by a fraction, then instead multiply by its reciprocal. So let's go ahead and I'm going to start by factoring the top part of this fraction. I'll get x minus 2 times x plus 2 over x plus 3. And then I'm going to take the denominator part and flip it over, but I'm not going to factor it yet, and rewrite it x squared plus 3x over x squared minus 4x plus 4. Now that fraction looks like it can be factored fully. So let's go ahead and factor those, and then we're going to find terms that will cancel. Again, so I'm rewriting the left part, x minus 2x plus 2 over x plus 3. And then the right side is going to be, I think I can factor out an x, so I'll get x times x plus 3. And I can factor that as x minus 2 and x minus 2. Now I'm going to go ahead and look for terms that cancel. It looks like the x plus 3's cancel and the x minus 2's cancel. So those will go away, and I'm left with x times x plus 2 over x minus 2. And that is your final answer. We call this factored form, which is usually fine. We will often say, though, which values is this expression not true, and we know it's not true when x is equal to negative 3 and 2. Now our final answer makes it look like just x equals 2 is going to be a discontinuity, but we have to look back to the original equation. So we'll look up here where we had our denominators, and either one of those denominators, any value that makes the denominator 0 is going to blow the whole thing up. So in this case, x can't be negative 3 or 2. Next problem, 2 minus 5x over x minus 9 plus 4x minus 5 over 9 minus x. We need to, when we're working with addition or subtraction of rational expressions, we need to get common denominators. And this one is pretty close to having a common denominator. We have to use our little trick of factoring out a negative 1, then we can turn one of those into the same denominator. So I'll rewrite the first term, 2 minus 5x over x minus 9. And then I'm going to factor out a negative 1 from the denominator of the second term. Now I'm going to have x minus 9s. Now what do I do with that negative 1? Well, it turns out if you have a negative 1, if you're multiplying the bottom by negative 1, you could just move that negative 1 upstairs and multiply the 4x minus 5 times negative 1 and leave x minus 9 below. You can only do that because it's negative 1. If it was negative 2, you couldn't do that, although you could make the negative go up. So what that will look like is 2 minus 5x over x minus 9, and then minus 4x minus 5. I just took the negative 1 and pulled it out in front of the whole fraction over x minus 9. Now I have the same denominator. I can combine like terms, put them all over one denominator, 2 minus 5x minus 4x plus 5, simplifying minus 9x plus 7 over x minus 9. And that would be the final result. And we could say that x cannot be equal to 9. And that's the only value where that is true. Okay. Graphing rational functions. So, graphing rational functions, we want to find asymptotes. So first we look for asymptotes. The vertical asymptote, remember, is wherever you find a 0 in the denominator. So when x equals negative 3, you're going to get a 0 in the denominator. So there's your first asymptote at x equals negative 3. And I've already plotted that with a dotted line. To find the horizontal asymptotes, you look at the order of the denominator and the numerator. In this case, they have the same order. They're both x to the first power. When they're the same order, you take the coefficient in front of the x term for the top and bottom and find their ratio. So in this case, it's going to be negative 3 over 1, which is going to give you negative 3. Okay, so negative 3 over 1 is negative 3. So there is your horizontal asymptote. Next, you want to plot intercepts. Plug in 0 for x and see what you get. Plug in 0 for y. If I plug in 0 for x to this function, I get 0 over 3, which is 0. So once I get a 0, 0, I know that is my x and y intercept. I can go ahead and plot that point. And the last thing is to just plot points generally. So make a little t-chart and just start plugging in points relatively close to your asymptotes to get a sense of what the curve looks like. So I'll plug in 1 and see what I get. I get negative 3/4. Negative 2 gives me 6, so that's looking like the curve for that graph. Now, where is the other curve? Is it kitty corner? Is it next to it above, next to it below? So plot a point that is negative 4-ish. We get negative 12, so then we get a sense of, by symmetry, where the other one is, and we can plot that graph accordingly. Next one, we have actually a higher order in the numerator than the denominator. First of all, we can find a vertical asymptote. A vertical asymptote, of course, is where there's going to be a 0 in the denominator, so that's going to be at x equals negative 1. But then, the horizontal, because the order is higher in the numerator than the denominator, we can't make any conclusions about a horizontal asymptote. But what we can do is factor the numerator and then see if it will cancel with something in the denominator, which in fact it does. The x plus 1s will cancel, leaving you y equals 2x plus 1. And that function, or g of x, that function we can then graph. It's a linear function. But what we have to be careful is where that, what we thought was an asymptote is not actually just a hole, and where that asymptote we thought was, there is a discontinuity in our function y equals 2x, because there is no allowable value at the value where x is equal to negative 1, because that would make a 0 in the denominator. So we have a linear function, graph y equals 2x, but we have a hole at that spot where x equals negative 1. Okay, direct joint inverse variation. If m varies directly as p, then we would write that as m is equal to k times p. And then it's helpful to solve for k to set up, ratios and proportions. So we would say that if m equals k times p, then k equals, and that's wrong actually, p over m, it's not p over m, it's k equals m over p. Okay, so then we just say m1 over p1 equals m2 over p2 and solve it that way. If s varies inversely, I'm going to scribble this out again so that you don't remember. That's right, it's wrong. As s varies inversely as t, then we'd say s is equal to k over t. If we solve for k, we're going to get k equals s times t. So then you could say s1t1 equals s2t2. Solve your proportions. And finally, p varies directly as t and inversely as v. Okay, so this is a joint variation. In other words, it varies directly with one variable and indirectly or inversely with the other. So we say p equals the constant times t because it varies directly, and then divided by v because it varies inversely as v. So if you want to solve for k, you're going to get k equals p times v over t. So you just set it up. P1 v1 over t1 is equal to p2 v2 over t2, etc. So let's do the example. T varies directly as r. When t is 12 and r is negative 2, find r when t is negative 8. Okay, t varies directly as r, so we'd write that as t equals k times r, or k is equal to t over r. And so t1r1 is equal to t2r2. So t1r1, we got the first t is 12, the first r is negative 2. So 12 over negative 2 is equal to t2r2. T is negative 8 over r, which we don't know. In order to solve a little proportion like this, it's easiest to cross multiply and solve. 12r is negative 16, positive 16. R is therefore 12/16 or 4/3. Solving rational equations. Now we have an equality sign. So we treat these differently than the expressions. In the expressions, we wanted to find a common denominator so we could add like terms. In equations, we want to get rid of the denominators altogether. So we need to figure out what factor can we multiply each term by so that the denominator will cancel in every case. And whatever you do to one term, you have to do to all of the terms, just to keep it equal. So in this case, the least common denominator is going to be x plus 2 times x minus 2. So let's go ahead and multiply each of our terms by x plus 2 times x minus 2. When we do that, we're going to get x plus 2 times x minus 2 times x over x plus 2 minus x plus 2 times x minus 2 times x plus 2 all over x minus 2. And then lastly, I'm going to get x plus 3 times x minus 2 times x plus 2 all over x minus 2. Now we'll go ahead and cancel out the denominators. That was the whole goal, is to clear out the denominators, get rid of them. And when we do that, we will see that we get x times x minus 2 minus x plus 2 times x minus 2, and that's going to be equal to x plus 2 times x plus 3. So we'll go ahead and multiply those all out. We get x squared minus 2x minus x squared plus 4x plus 4 equals x squared plus 5x plus 6. Simplify, combine like terms, see what we get. Subtract 16x from both sides, subtract 4, or add 4 to both sides. X squared plus 11x plus 10 is equal to 0. Now that one we could solve with quadratic formula, or we could check to see if it factors what multiplies 1 times 10 and 11, so we get two answers. We get x equals negative 1 and 10. And remember, it's really critical whenever you're doing a rational equation to check your answers. So let's plug negative 1 in. Negative 1 over negative 1 plus 2 is negative 1, so we get negative 1, I'm sorry, it was plus 1, so we get negative 1 minus, plug in negative 1 plus 2 is 1 over negative 1 minus 2 is negative 3, so minus 1/3. Is that equal to negative 2/3? And in fact, it is, so that one checks. We also have to check x equals negative 10. I plug in negative 10. Negative 10 over negative 8 minus negative 8 over negative 12 equals negative 7 over negative 12. Is that true? No, in fact, it is not. So that minus 10 is an extraneous solution. It is not part of a solution set, so we can ignore that one. Okay, let's do an inequality. This is the last problem. Trick here, remember, first identify the zeros of the denominator. That's the first critical point. Those are where you're going to have your discontinuities, so do that first. Then set your inequality to an equality, make it an equal sign, and solve it. And then plot your hole, or your anomaly, and then discontinuity, and then the number that you get for a solution, and then check the regions around it. So in this case, p cannot be equal to 0. Let's go ahead and solve, though. Plus 4 over 5p is greater than 3/2. We want to get a common denominator. We want to clear it. So what are the factors? Well, we got a 2, a 5, and a p. So let's go 10p. Let's multiply both sides by 10p, each term. So when we do that, 10p and 2p, those cancel, and we're left with a 5. 10p times 4 over 5p, that can cancel, and we're left with an 8. And lastly, we have 15p. So we get 13 is equal to 15p, or p is 15, hold on. P is, 13 over 15. So now we can go ahead and plot those 2 points, the whole and the value that we found, 13/15. Now we need to test some values to see what's happening in the regions around them. So we start by testing 1. When we do that, we figure out we get 5/10 and 8/10 is 13/10. That is not greater than 15/10, so the answer is no for the region near where the 1 is. Next we're going to try 1/2. In that case, we get 1 plus 4 over 5/2. Is that greater than 3/2? So 1 plus 8/5. Is it? Yes, in fact, it is. Because we're going to get 16/5 compared to 15/10. So that's close and a little bit bigger. So that's a yes region. And finally, we test negative 1. Negative 1/2 minus 4/5 is greater than 3/2. No, it does not. So we will not plot that part. Now notice I put open circles at the 0 because that's a discontinuity. P equals 0 can never be true, so we leave that as an open circle. 13/15, that is also an open circle because we're dealing with an inequality that has a greater than sign as opposed to a greater than or equal to sign. And that concludes our review.